Okay, so the session is now being recorded. Um, so once again, hello everyone. Thank you for joining us today. Our facilitator for today would be Francis de la Cruz of the Optics and Instrumentation Research Lab, who's worked with various programming languages and various simulations in physical systems, most notably in electromagnetic systems. So without further ado, Francis, you have the floor.
So, hello everyone. Can you hear me clearly? Okay naman, my
Yes,
voice.
audio is okay.
So, can you see the screen? Is it, is it not blurred or okay? So, welcome to our MATLAB short course of creating plots and graphics in MATLAB. So, MATLAB short course part 1. So, this is the introduction to MATLAB graphics by yours truly. I'm Francis S. de la Cruz. And uh, this is brought to you by DOSTP shirt, sa University Manila, the Metamaterial Biosensors Group, also the DLSU Optical Society, the Optics Research Group, which means Optics, Photonics Technology, Instrumentation, and Conservation Science Research Group, and of course by EM Possible through the University of Texas, El Paso, Dr. Raymond Rao. Okay, so now let's start our short course. So this is our short course outline. Part 1, MATLAB graphics, and of course we do have part 2, which is building geometries into data arrays, but it would be on another time. So today we will tackle about 1D graphics, okay, the MATLAB interfaces, how to make plots and diagrams. We also have 2D graphics. Okay. For the part 2, which will be in the future, we will going to build some data arrays used for numerical methods and some useful tips and tricks. Next is our prerequisite, okay, for this short course would be a basic understanding of MATLAB syntax and how MATLAB works. Also, basic coding experience, whether in Python, C++, C, okay. But it doesn't actually matter because I will try to explain each line of codes that we're going to use. And also, Paolo will give a link for the learning materials, including the PPT, the the notes, which is the PDF version of your PPT, also the codes for 1D graphics and 2D graphics, so that you can actually uh, you can actually you can actually look at the codes and then understand it and then try to implement in your MATLAB. Then for the software, okay, the software would be MATLAB version 2017 and above. Okay, so as of now for DLSU students, the available license for MATLAB would be R2022A or B, I think. That's the latest version of MATLAB. So there's nothing to worry about. And for people that doesn't have any access to MATLAB, we have an open source software called GNU Octave that they can run MATLAB codes. But of course, this GNU Octave is a little bit less powerful compared to MATLAB. But still, your basic MATLAB graphics can still run. And I already checked it, but there are some differences. But if you really want to use GNU Octave or as a substitute, there's no worry about that. So today, we will learn the fundamental blocks of making graphics, and the rest is up to you or up to us to explore and discover. So our discussion of each lines of code, how does it work, it would be a little bit detailed. So let's continue. So this is the MATLAB interface. Okay. So if you look at your MATLAB interface when you open it, okay, so this interface is a little bit configured already. So you have the MATLAB window editor, you have the MATLAB command window, you have the MATLAB workspace, and you have the MATLAB graphic window. And I think it's obvious what these windows do. Okay, so for MATLAB editor window, you can write codes, you can write programs that you can run in MATLAB. For MATLAB command window, it can act like a calculator. Okay, if you have some commands that you knew, you can try it you can enter it, and then it will give you immediate results. Okay. For MATLAB Workspace, it includes all of the variables that you define, okay, when you are doing some kind of programming. And for the MATLAB graphics window, if you want to display something, you want to display a graph, a plot, or a figure, you can use the figure window, the graphics window of MATLAB. So let's go to our MATLAB. Okay. So for now, I will use the So this is the configuration. So if you open, for example, your MATLAB is fresh, okay, freshly installed. Okay. The first thing that you will see is this. Go to home, the layout. Okay, so in the layout, there's what you call default. So if you open your MATLAB fresh from installation, this would be the basic or the default configuration of your layout in MATLAB. And technically, there's a lot of layouts that you can play with. You can have, okay, just select in the home tab, and then in the environment option, then you have the layout button. You can check default, which is this one, the 2-column, like this one. You can also have all but command windows. Everything is closed except for the command window. And you can have the, well, I call it fancy style. I mean, this is just my configuration, or the earlier configuration, like this one. So it's all up to you. You can save your layouts actually. So if you're comfortable with that layout, then it's fine. So these are the windows that we need. So we need the editor window, we need the command window, we need the workspace window, and you can actually move them around. You can move the command window here. You can move the, I think this one stays here. I'm not sure why, but you can move the workspace here and so on. Okay. You can also dock and undock your tabs. So for example, you have the command window here. Oops. Let me undock this. So it's actually here. So there's an option here, the very far. Then you can choose undock or Control Shift U. Okay, so you can have a shortcut, Control Shift U, to undock the windows. For example, this command window was undocked. You can also redock it again or dock it again in the MATLAB interface. You just go near here, near the X symbol, near the close. Just below it, you have the new command window action. You can choose dock or Control Shift D. Okay, so already dock. And you can again rearrange your layouts. Okay. So for me, the layout that is nice is this. Oh, sorry. Just move it here. Okay, so dock all in editor. Oh, I will just use the home and layout Francis style. And then move this one. So it's all up to you. You have all the freedom to arrange your layouts if it will fit your best interest in coding. Okay. So this is the MATLAB interface. Okay, and later on I will show you the figure window. Okay. So for now, we will use the command window. So let me use it here. So I have the command window and the workspace. Okay. So going back. Okay. So for MATLAB resources, okay, so let us remember that this is just an introduction to MATLAB graphics. This is not purposely, or the purpose of this short course is not to introduce MATLAB to you, but actually use MATLAB for creating graphics, okay, or presenting plots, presenting images, and such. Okay. For us to understand MATLAB deeply, know the fundamentals of MATLAB, we can visit the MATLAB Academy at matlabacademy.mathworks.com. Okay? And if you have a MathWorks account, okay, or you have an institutional login, you can go to mathworks.com/learning/training.html. So there's a lot of things to learn in MATLAB Academy. Of course, if you are into electromagnetics or computational electromagnetics or any other EM-related stuff, you can visit the empossible.net website. This is run by Dr. Raymond Ram. So we're so grateful to Dr. Ram for allowing us to use his resources, and it really helped us to understand further electromagnetism and move our research further. Thank you very much, Dr. Ram. So don't forget to visit the EM Possible, and you can see a lot of materials out there from microwave, engineering, antenna engineering, computational electromagnetics, metamaterials, and so on. And next, if you want to know your commands, okay, you can go to MATLAB command prompt, okay, and then just type help and then the name of the command. So later on, I will show it to you, so don't worry. And finally, okay, I encourage all of you that if you are willing to use MATLAB, okay, just make projects using MATLAB. If you really want to be proficient in MATLAB, just keep using it. Okay, not every day, of course, but just try to use MATLAB in your day-to-day projects, especially if you are dealing with scientific computing. So let's go to the main topic, introduction to MATLAB graphics. So we're going to use two defined functions or two distinct functions. And these functions are very important in creating MATLAB graphics. Number one is the plot, and the second one is the image SC. For the plot, you can make linear plots, you can make figures and such. For image SC, you can plot two-dimensional functions and such. And we will go into details in using this. Okay. So next. So before we start, okay, I would like to make clear about these commands. Okay. So for example, you want to create an array. So an array is a collection of numbers. So for example, 1, 2, 3, 4, 5. So it's a 5 by 1 array. It means that it has 5 elements, 1 row. Okay. So there are 5 digits in a certain collection. 1, 2, 3, 4, 5. So for example, I want to do that in MATLAB. There are two ways that we can do that, using the linspace and also using the direct array. So for the linspace, you can specify a start. Okay. So what number you will start? So for example, 0. Then the end number, which is the stop, and say 5. And then let's define the number of points, okay, in that array. For example, 5. Okay. So if you use linspace, you start from 0, you end at 5, and then you have 5 elements. 1, 2, 3, 4, 5. Okay, so 0, 1.25, 2.5, 3.75, and 5.0. Take note that in this array, you can control the number of points. There are 5 points. Second, you can control the endpoints position. Okay, so you can control 5, 6 until at what number it will stop. But the problem is this: you cannot control the number of steps, because if you want the step to be 1, you cannot define it in the linspace. So the distance between 0 and 1.25 is 1.20. So it's hard to control the step size. But if your application needs to control the step size, you need to use a direct array. So for the direct array, you have a start, you have a step, and you have a stop. Okay? So for a direct array, you have a start, you have a step, and a stop. So what is the advantage of the direct array? For the direct array, it is easy to control the step size. For example, the step size is 1. You start from 0. So there would be 0, 1, 2, 3, and 4. What is the disadvantage of a direct array? It would be hard to control the number of points. Take note that, for example, you want to have an array of 5 elements. Running from 0 to 5 will give you 6 elements. So 0, 1, 2, 3, 4, and 5, which is 6, including the 0. Okay? So it would be hard for you to control the number of points. Also, it would be hard to control the last point, the last point position, since if you want a 5-element array, you don't need to include the number 5. You will just put 4, 0, 1, 2, 3. So this linspace and direct array has different applications, and we will start using the linspace. So let's go back to our MATLAB. So for our MATLAB, okay, we will use first the command window so that you would be familiarized with using it. Okay. So first, you have the MATLAB, you have this MATLAB interface, you have the command window, you have the workspace. You can see all of the defined variables in the workspace. So for example, I want to make an array of numbers, and I will use linspace. Okay, so linspace command, start is 0, and then start is 0, and then the stop is 10. Okay, oh, sorry. And then the amount of points, okay, or the amount of elements in the array, let's say 10. If I enter it, you can see in the command window that there are some numbers here. Okay, so columns 1 through 6 and columns 7, 10. So what does it mean? Okay, it means that these are the elements of your arrays: 0, 1.1, 2.2, 3.3, up to 8.8, 10. Okay, as you can see, you can control the starting number and you can control the end point, but you cannot control the step size. So if we increase this to 100, of course, there would be 100 points. Okay. So that's the first array. So what's the use of that? Let's define a function. Y is equal to, let's say, x squared plus 1, probably. Oh, yeah. Maybe x squared, or I will just try to define another function. X plus 1, say cube. Okay. Take note that if you are using MATLAB, if you don't want to display the result in the command window, you should put a semicolon. Without a semicolon, as you can see here in the X array, when I hit enter, it prints, it displays the contents of the X. Okay? But if I put a semicolon here, oops, there's an error. Okay? So what's the error? Incorrect dimensions or raising a matrix to a power. Take note that in MATLAB, everything is a matrix. When you do an operation, everything should be done in a matrix operation. But in this case, we don't need any matrix operation. We need what they call the element-wise. Okay? Element-wise operation. There are different kinds of element-wise operation, like multiplication, division, power. Okay? So we need to put a dot before the operation. So y equals x plus 1. Okay? And then dot, then raise it to 3. And then put a semicolon. And as you can see, it will not display the answer. But as you can see here in the workspace, it was defined. A variable was defined, as you can see in the workspace. Okay? So this function can be plotted. Okay? So how to display this? How to display this y of x? Let us use the plot function. So the plot function requires two inputs, x and y. And if we hit enter, you will see this figure. So let me enlarge this. Tada. So this figure shows you the function f of x, or the y. Okay? And as you can see, this figure is pretty bare, pretty boring. Nothing is here. I mean, you have the plot, but if you're going to submit this in a publication and such, or you're going to make a beautiful plot, let's say it's your purpose, this will not cut. I mean, it's pretty bare. Thin lines, okay, no labels at all, everything. So how can we manipulate, or how can we change? How can we design this figure window? Okay, we need to use oops, this one, handles. Okay, so there are three things that you need to remember when you are dealing with MATLAB graphics. Number one is the handle, the second one is the get command, and the third one is the set command. So what is the handle? The handle is technically you're assigning something to a handle that helps you to access all the properties of that function. So for example, the plot function. If you assign the plot function to a handle and then you use a get or a set, it will help you to access all of the properties of the plot. Next is the get. For the get, you can use the get command for you to show all of the changeable properties, all of the available properties that you can change in a certain math. And for the set, if you're going to use the set, you can actually change the values of the properties. So let's have some example. Oops. So let's have some examples. So first, we define a handle to our plot. Okay. So let's call the first handle to be line plot. Okay. So line plot is equal to, or you assign something to a line plot. So let's say you assign the plot xy to the line plot and you hit enter. What you can see, line with properties. What does it mean? Let's use the get. Get means get the properties, display the properties here of the line. What you can see here, this is all the properties that you can change, okay, that you can manipulate for the line plot. What does it mean? So look at the figure. Look at this figure, and everything in this line, this blue somehow thin line, okay, every property that you can control here can be seen here. So by just using get line plot, you can display all of the properties of this blue line, right? All of the properties of this blue line. The next, how about I want to change the plot axis. I want to change the figure window. I want to change the color of my background. How can I do that? Here, it comes a special property of this commands, okay, which is the parent, okay? So later, we will try to manipulate your line plots, your figure windows, your plot axis by using the parent. So what is the parent? Going back. So parent property. So from here, technically you have a figure window, you have a plot axis, and you have a line plot. This is what it looks like when we try to extract the parent property. So you start with the line plot properties. Okay, so you have a handle, and then you have all of the properties of the line. Okay, and then if you get the parent of the line plot, it will give you the plot axis. Okay, it means that if you have the plot axis properties, you have the power, or you have the capability to control all of its properties. The next is that if you get the parent of the plot axis, it will give you the figure window. It means that you can now control the figure window properties. That's right. So here, going back, so take note that we already have a handle for the line plot. Now, we need a handle for the plot axis and for the figure window. So let's name it as plot axis, okay, which is equal to use get command, put the line plot as an argument, okay, and then the line plot property would be parent, okay. So plot axis equals get line plot. You get the parent property from the line plot. It will give you the properties of the plot axis. Okay, so let me enter that. And for us to be sure, use get plot axis. And as you can see, it reveals, it shows, or it displays all of the properties that you can manipulate, okay, for changing the plot axis. So you can change the grid color, you can change the font name, font size, line width, and so on. There's a lot of things that you can change here. Okay? Even the grid color, you can change it. Okay, and as of now, these are all the default values. Okay, and for what if you want to change the figure window? So of course, let's get a handle, figure, and then use again another get. Okay, and then we started from the line plot, then now we are the plot axis. Take note that the parent of the plot axis is the figure window. So we need to extract the property, okay, of the figure window from the plot axis. So plot axis, okay, parent, and then hit enter. Okay. As you can see, these are the properties of your figures. You can click the show all properties. It will be the same as get, okay? But I prefer using the get command itself for you to practice. Okay. So get figure, and you will all have the options to change. So you have the color. Okay? You can change the color. As of now, the default color is 0.94, 0.94, 0.94. What does it mean? Okay, so if you look back at the figure window again, okay, 0.94, 0.94, 0.94, it is like an array of 3 numbers. The first element represents the red. The second element represents the green. The third element represents the blue. Okay, so this number running from 0 up to 1 will scale your red, green, and blue. So it means that since this is gray, a little bit closer to white, it means that the RGB values would be as close as possible to 1. So 0.94, 0.94, 0.94. So that's why it's color gray as the default. And you can actually change that. Okay. So now we all have the handles. We all have this plot axis, line plot, figures, and we have now all the properties that we want to change. Right? How we're going to change these properties? That's where the set command will come in. So here, there's an example modifying the figure window, and in your left side there is what you call the set. Okay, so there's something that you need to do with the set. So let's just do that. Okay, let's go back. Okay, so for example, I want to change. Let's look at the figure first. For example, I want to change the thickness of the line plot. Okay, I want this to be thicker, because I cannot see it. If you put it in a paper, in a publication, and this is your line, probably your reviewer will just go back and please put a thicker line or a higher resolution image for your plots, because we cannot see it. So let's go back here and let's put set. First is that we already have a handle. Okay, so handle for the line. Okay. So let's for example, we use set in the plot, and nothing, I mean, you don't modify anything, you just press enter. What will you see? You will see all of the properties and the available options. So for example, line style. So the line style property of the line plot can have these options. You have a continuous line, you have a dash line, you have a dotted line, you have a dash dotted line, or it can be none. Okay, I think the default is the continuous line. Okay, for the line width, you don't have any option because it actually requires a numeric scalar. It means a number. For example, line width equals 2, 3, 4, 20, 100. So let's try to change these properties. Okay, so for us to see the line better. So set okay, line plot. So the handle is line plot. Then line width. I want to make it thicker. Let's say 20. Will it be so thick? So let me press enter. Oh, it's so thick. Okay. So probably we need to reduce the thickness. Let's say, okay, there's another shortcut. If you don't want to type everything, you just need to hit the up button, the up key. Okay, you can go back to your previous entries in the command line. So let's change it to 2. Then let's hit enter. So what will happen? As you can see, you have this line here. Okay, so this line here is now a little bit thicker than before, than initially, but less thicker compared to the 20 line width. Okay. So it means that we can change the properties of the line. Let's say we want to change its line style also. So again, we type the set, we can press the up key, then remove this line style, line width, remove the line width, replace line style, and then put the desired option. So what are our option in the line style? This one, right? So you can choose a dash line, dotted line. For example, I want to choose the dash dotted line. Then I will put it here. So strings, so dash dotted, and then hit enter. So what would be? So as you can see, if it's not so visible, it is now a dash dotted line. Right? So any questions about this one? Dash dotted line. So we are changing the parameters. Okay, so we are changing the parameters of the line. How about we want to change the parameters of the plot axis? Then we're going to look for the line. We're going to look for the plot axis, plot underscore axis, and all of the available properties. Okay. So for the plot axis, you have these properties with their options. Okay. So y-axis location, left, right, origin, and so on. So for example, I want to make my plot axis thicker. So the lines or the borders to be thicker. So let me look at the properties. Maybe there would be some kind of line width, okay, property, which is this. Okay, there is a line width here. And then I will just try to change the thickness of the plot axis. So set again, then plot axis, and then line width. Okay. Then set it to, let's say, 4. Okay. Then hit enter. So what will be our plot will look like? Oh, as you can see, the plot axis becomes thicker, like this. So you can change the plot axis. And there's a lot of properties that you can actually change. Okay. Next, how about the properties of the figure? Okay. So set figure. Okay. Set figure. And then let's hit enter. Okay, there's a lot of this. For example, I want to change the color. Okay, I want to change the color of the figure. As of now, the default is a little bit gray. Okay, so I want to change this some kind of blue. Okay. So for us to do that, first is that we look at the properties. As you can see, X by 0 cell. So later on, I will explain to you what does a cell mean in a MATLAB. But as of now, the color needs some kind of array, just like what I've said earlier. An array with 3 numbers that controls the color red, green, and blue. Okay. So we will declare that. So let's say color. Okay. Color equals an array of 3 numbers. Since I want it to be a little, a bluish color, so I need my red to be somehow less, so 0.1. And then somehow the yellow would be at half, 0.5. Take note, the number is running from 0 to 1. And then for the blue, would be around 0.9, near blue. Okay. So this would be our list or array. So hit enter. And then let's use the set. Okay. So set figure, and then get the property which is color. Okay. And then use this color, okay, this color array, okay, to change the color of the figure. And then let's hit enter. When we hit enter, tada, it's color blue. Okay, so these are the basics of get and set. Technically, if you mastered how to use the get and set, you will be a master of changing the colors, the graphics, everything, the properties of your figure window, even the line, and making your plots more beautiful. Okay, but of course, we're not going to use the command window all the time because it would not be like some kind of programming. Right? Sometimes we need to write scripts. Okay. Actually, there are other things that I want to discuss here. For example, is this. Okay, changing properties. Okay. Oh, let's go back. Okay, so first is we have the plot controls. Okay, so the plot command. You can plot one-dimensional data and such. But we can also plot two-dimensional data using image SC. So now I will show you, let's say, a random numbers of an array, a two-dimensional array of random numbers. So first is that I will declare matrix. So A is equal to rand. Let's say 50, 50. What does it mean? It will give you a matrix of numbers from 0 to 1, but the dimension is 50 by 50. 50 rows, 50 columns. Okay, and each element would have a random value from 0 to 1. Okay, so don't put the semicolon, then enter. So you will have this one. You can check it in the workspace if it works. So as you can see, all of these numbers will never be less than 0 or greater than 1. It will run from 0 to 1. So all of these numbers, okay. 50 rows, 50 columns. Okay. The next is that I want to display this. I want to display this in MATLAB. I will use the second function that we're going to use, which is image C. And then I will just use A. Hit enter. And what would be the figure look like? Tada! So this is the figure. All random numbers. Okay. So it looks like noise. Okay. So for example, I have this 2D figure. Of course, this is not the same as plot. This is another command. But I want to change the plot axis. I want to change the figure. I want to change the or to change everything. Okay. How can I do? Okay. So take note that we're going to use, or we're going to do again what we did dun sa plot command. So we will have a handle. Let's say image handle, okay, or images. Image SC. Okay, so all of the properties of the image. Then, for example, I want to change the plot axis, okay, of this image XS. Of course, we need to get the parent of the image SC again, so that we will have an access to the plot axis. But there's a shortcut for this one. We can use what they call the GCA. Set GCA. What do you mean by set GCA? GCA means get current axis. Get current axis. So it means that it will retrieve all of the default configuration or the current configuration of the axis. And then if you put it in the set, you will able to change the values of these current values. Okay. So for example, GCA current axis, or all of the properties there, I want to change the line width. Example, I want to make it thicker. So since we already knew the line width, okay, let's make it 4 again, and then hit enter. It will show a thicker, right? A thicker line bounding the image SC plot. For example, I want to go back to the original colors, which is the default is 0.94, 0.94, and 0.94. We can again redefine the color. So first is color again equals 0.94, 0.94, 0.94. Okay, then hit enter. And as you can see, it will overwrite your workspace. Okay, so this color, when you assign another value, it will be overwritten. Okay, and then let's set the figure again. Okay, so the figure, then color again as a property, and then put color again, and then hit enter. So what will be figure? So it goes back. Okay, it goes back to being gray. Okay. So that's how we control our figures, our plots, and everything. Okay, so this is the power of the get and the set. Okay, but there's something I want you to notice. Okay, so look at Perry. So we go we go further. Okay. So let's first set the font size of the plot markings. Okay. So the plot axis again, or let's just use GCA. Set GCA, then get the font size. Okay. And then let's increase it to, let's say, 16. Because as of now, it's a little bit small. Okay. So let's hit enter. And what you can see is that there's an increase. We can increase it further. Let's say 30. Might be overkill, but the larger the better. Okay, what can you observe here? You can observe here that for the x-axis, it's okay. 0, 10, 20, 30, 40, 50. But for the y-axis, it's inverted. It's starting from 50, then we go up to 0. Okay? If you are dealing with Cartesian coordinate system, this is not the configuration that you want, right? This is not the thing that you want to use. You want the y-axis to be starting from 0 and above. So how can we change this? So let us look at the current axis configuration. So again, set PCI, hit enter. It will display all of the properties again. And then let's look for a property called wider. So what is wider? The y direction. And there are two options here. The first one is the normal, and the second one is the reverse. As of now, as a default, your plot is set to reverse. That's why it's starting from 0 down to 50. For us to make it like a Cartesian coordinate system or your XY plot, we need to set it to normal. Okay, so set, again, GCA, and then wider. Okay, and then normal. Hit enter. So what can we see? Tada. Okay, it's now going back. 0, 5, 10, 15, 20, 25, 30, 35, 40, up to 50. So that's how we change the ordering. Take note that you can change a lot of properties. Again, you can change the tick marks. As you can see, this is not uniform. This is by 10, 20, 30, 40. This is by 5. And later on, I will show it to you when we go to the proper scripting of 1D and 2D graphic. Okay, so let's go back to the PowerPoint. So here's the use of GCA, as you can see, and you have the wider also. So now we can flip it. Okay, flip it. So the direction. So from 0 to 5 downward, from 0 to 5 upward. The question is this: why is it doing like this? I mean, why MATLAB do this? Okay, is it because of its nature? Of course, yes. The answer is yes, because MATLAB means matrix laboratory. So it's a combination of math and lab. So everything in MATLAB will be seen as a matrix or an array of numbers. Okay, not anything about creating what do you call this? A point in a space, because it's not a Cartesian, right? So what MATLAB sees is this: so you have a matrix here. So your matrix has m rows, okay, 1, 2, 3, and of course number of columns n. Okay, and if you feel, okay, let's say you want to visualize this matrix using image SC, you will see this one. Okay, so the data inside A11 will be plotted here, and so on. So it means that it always starts from the top, going down to bottom, and that's the nature of matrices. But it is not something that we want. We want a Cartesian coordinate system if it's it is based on our application. So we need to flip the entire matrix, or we need to flip the entire image SC using the wider. So it would look like plotting a function f of x. Sometimes I'm not particular with this. Sometimes I will just let it from 0.5 to 3.5 and so on. Okay, I will just use the matrix understanding of MATLAB, not changing the wider. It's okay, it's still the same. The math is not that complicated. But if you do not feel If you do not feel like that, you're not comfortable in using that 0 to 5 down to 3.5 or inverse or reverse orientation, then you are free to use the wider pulse. Okay, so that's the MATLAB graphics for using the command line. Okay. Also, there's another thing. I think I want to show it to you. So going back to our code, we can have a color bar. This is really important. So if you have a figure like this one, you can set a color bar. Okay. So this color bar tells you the values inside this matrix. So the dark ones would be near 0, while the really bright yellows will be near 1. And also, you can configure this color bar. So you can get the color bars properties, and it will give you a lot of options again. And for example, I want the font size of the color bar to be changed. So I will just use set and then type color bar, and then change the color. Change the font size. I mean, font size, and then change it to something like, again, 16, a little bit bigger. And if I hit enter, you will see, oh, there's no change at all. Probably oh, it's because 27 is the basic. We might need to assign a larger number. Say 4. Yeah, look at this. So you change it. So the default is 27. So you use a higher number, which is 40. So to see the results. Okay. Any questions from the audience? So you can still follow. Okay. So I think this is the end for the using the command window. Most of the time when we do programming in MATLAB, we use the scripts or we use the editor window. So let me put this one here back. Okay. And let's show the editor window. Let's go back here. And we're now going to create 1D plots. We're now going to write. So this is what, probably this is our goal. Okay. But of course, this is not the end for all of you. I mean, you can still refine this graph, find this 1D plot based on your liking, okay, or based on the requirements of the, for example, the publishing house and so on. Okay. So first is that if you want to plot a sine and cosine function, we need some kind of array that runs from 0 pi to 2 pi. Remember, sines, cosines are trigonometric functions. So from 0 pi to 2 pi. So let's go back to our math. Okay. So for anything, okay, we want to initialize our MATLAB. Okay. So first is that a comment. If you want to write a comment in an editor, you put a percent sign. So it means that it will not be read by the program. So for example, 1D graphics. Okay. So I already saved this, but later on in the 2D graphics, we will save another file. Okay. The next is we will initiate MATLAB. Initialize MATLAB. So what do you mean by initialize MATLAB? First is that we need to erase or we need to close all open figure windows. Okay. Second is that we need to clear the command window. And next is we need to clear the memory of MATLAB. Okay, so close all. So all of the figures, okay, all of the graphics window will be closed. Okay. Then next is CLC. CLC means clearing the command window. If we enter that. And then clear all for the memory. As you can see, there's nothing happening because I haven't done it yet. But if I press F5 or in the editor, you press the run button, you can see, you can remove everything in your workspace and in your command window. So that's how I initialize MATLAB. Okay? So that other values in the memory will not interfere to my calculations further. Okay, so this is how we initialize MATLAB. The next is that let's calculate a function. Let's define a function in MATLAB. So calculate function or functions. Okay. So if I want to plot a sine and cosine, okay, so first is that I will define a certain number of points. Let's say 10 points. Okay. And then of course the argument for sine and cosine would be some kind of angle, which is theta. So theta equals, I will use linspace to create an array. Linspace, okay, 0, then 0 is the starting point, then the endpoint is 2 pi, and then the number of points for that array would be 10, which is n. Okay. Then put a semicolon. The next, define function 1, okay, which is equal to sine theta. Okay, it's like how we use that. And f2 equals cosine theta. Sorry, cosine theta. Okay, so what to do here? Next is that somehow I want to align my equal space, my equal sign, so that it would look neater. Okay, so like this one. So I have now this function, okay, and I don't have any way to plot this, okay, except for using the plot command. So before anything else, I will just press F5 or run it, so that I could see that there would be no errors. So no errors in the command window, so everything is fine. And then let us display the plot function. So let us use the plot command. So of course, the first what do you call this? The first argument would be like the x-axis. So the array, the entire array of your x. So if you're going to plot the sine and cosine function and your x is theta, so the what do you call this? This array would be the first argument, theta. It would be the x. And then for the y, that would be the values of your sine and cosine. So let's say f1, okay? And that's it. Let's try to print this. Run. You will see like this. So it's an ugly looking plot, as you can see. I cannot move my plot. I'm not sure why. How to remove this Doctobot? Oh yeah. So this is an ugly looking plot, and as you can see that the lines are jagged. Okay, so it's not perfectly smooth sine curve. Okay, so if we go back to our PowerPoint, okay, this happens because of the plot resolution. The plot resolution is not that high. Okay, so the number of points is only few, but if we increase the number of n, the resolution of the plot will also increase. It will be high resolution. You will get a smoother curve. So let's do that. So let's increase this to, let's say, 100. Then hit. So now you have now a much better looking plot. Okay. Like this. So also we can change the line width. Okay, you can change the line width. We can also change the lines. Okay, let's do that. So first is that I want it to be okay. Okay, so another feature of the editor, also another feature of the function, you can already change the properties inside the plot. Okay, so initially you have a handle, and then you use the handle to the get and set. Okay, later on we will use the set, but now we can directly change the properties of the command within the command itself. So you will just need to put some arguments. So for example, I want this to be a straight line, but color black. Okay. So there are different formatting for this. So for example, a line, continuous line, you have a dash line, you have a dash dotted, it can be a dotted line. Okay. While the second character will give you what? Will give you a color. You can make it cyan, you can make it green, you can make it red, you can make it black, or sorry, this is blue. B is blue, K is black. Okay. So I want it blue. And then let's change the line width. So we declare the line width. Okay. And then after the line width, you put the number. For example, I want it 5. Okay. And then let's try to run it. As you can see, it's now thicker. It's now more pronounced. Okay, it's thicker now. So we're going to do this with the cosine function. So I will copy this and then hit enter. Okay. And then let's press enter. Of course, I want it to be cosine. Press F5, run. Okay. So what can you see? You can see this function. But this is a cosine function. Saan napunta yung ating sine function? So the sine function is somewhere here, but it's not actually in the figure. It's because the second function cosine, the second plot, overrides the first. Okay. So nasa ibabaw siya. So it is over the first plot. Okay. So you need to use the hold on and hold off. So what is the hold on and hold off function? Okay. So when you use the hold on, it means that it will stick to the first, okay? And then the second plot will be put on it, okay? So if we hit F5, you will see 2 plots. And I want to change the color, okay? Let's say the cosine plot is red. Okay, run. Okay, so you have 2 colors. But for example, in a publication, you just need a black and white, okay, print of your plot. You cannot distinguish these 2 plots. You cannot distinguish the sine and the cosine function. So somehow you want to change the line style. So by changing the line style, for example, for the cosine, I want it as dashes. If I hit F5, you can see that now my lines are now dashed and continuous, blue and red. So whether it's in the publication it's black and white, you can still distinguish the plots. Okay. So what is the effect of hold on and hold off? Okay. So if there's no hold on, your cosine will be just printed over the sine. It will just the background, you cannot see the sine. You just see the cosine because you don't have any hold on. But if you put the hold on, okay, if you put the hold on, you will see the figure earlier. There's a combination of sine and cosine. But what if you have you don't have any hold on? So for example, you have many plots and you don't have any hold on. This would happen. For example, I run a code here. Okay, don't worry if you don't get it at first. So you have this for loop. It will just repeat and repeat and repeat the command inside. Okay. So as you can see, there are 2 graphs, cosine and sine, and without a hold off, the plot will continue to overlap. Okay. So if you want the plot to be to continue to overlap, do not put hold off. Okay. Just put hold off if you decided to stop the plotting, the combination of plots in a figure. Okay. So as of now, I want it to be hold on and hold off. You can also add another plot and so on. So for example, I added another plot. So I need to copy this. Okay. Need to copy this. Of course, I need to copy the hold on. So this is the third plot. Okay. Let's say F1 plus F. F1 plus F2. So I added 2 functions. And let's call it as let's say color black and then dash dotted. Okay, so F5. So as you can see, the block line here is the sum of the two functions. Okay, so you have three functions here. This is the basics of the 1D block. So does anyone have questions? Okay, so Ponti, you have a question. So how do we get the window you're using, the one different from the new script? Yes, correct, new script here. So you can press the new here or press the down button, then script. Okay. So thank you, Ponti. So next. Okay, so you have the figure here, but somehow you want to make things right. Somehow you need to make this more beautiful. For example, you might want to increase the thickness of the borders, or you want uh larger tick marks, or you want to control the tick labels, you want to put an X label, a Y label, you want to put a title, you want to remove these unnecessary white spaces. So, the plot stops here and there's a blank space here. So it's a little bit ugly. Then, for example, another example is that, so I will just remove this first and then play it again. So for example, you have this plot, okay? And then as you can see, the peaks of the plots and the trench, okay? So the peaks, the crest and trough, the crest and trough of this wave are really near, or it's intersecting already the boundaries. I want to have a small space there. I want to have a small or a short white space up here and down the bottom. Okay. So if you are dealing with, for example, S11, reflectance, transmittance, plots, and so on, you might want your plot to be, you have some kind of space above so that you would see what is the value of this one. Okay. So we will do that. We will try to change the view of your figure. Okay. So now let's proceed to set view. Okay. Set view. So take note that in this figure, it's a little bit rectangle. It's not square, or somehow there's a white space here. Okay. So how can we remove the white space here? Okay. So there's a command called axis, and then just put the word type. So axis type. So if we press F5, okay, what you can see is that you just remove the white space. Okay, so you don't need that. So it means that when the function ends at this point and you put the axis type, the bounds of your plots will be at the ends. Okay, this is the both sides, left and side. Okay, sides of your. Okay, so that's the axis type. Okay, we can also control the font size. It's a little bit small, so we might want to increase that. So set, again, GCA, the get current axis, and then the property, which is font size. So let's change the size of the numbers or the label of the tick marks. Let's say around, let's say 30. So if we hit enter, it's a little bit huge, let's reduce it to probably 17 or 18. Okay. Press run again. And as you can see, probably okay. You can see here. Okay. Then next is, how about the axis? How can we limit the axis? For example, I already want to put a white space, some space above 1 and some space below. So if you want to do that, okay, I will just put some enter here so that I would have more space to code. Let's define the X and Y axis. So first is the X axis, and the second one is the Y axis. So first is that I want to adjust the limits of my Y axis. If I want it below 0 or above 1, okay. So I will use a command known as lim. Okay. So lim will give me this one. So lim from this one. So lim, y lim, it means the limit of y. So the lower bound, y mean, would be below. So minus 1.1. Let's look at the figure first before we try to put some kind of figures. So let me increase this. Okay. So take note that your y-axis runs from 1 to -1. Okay. So that's the nature of your sine and cosine. It runs from 1 to -1. Okay. And your x-axis runs from 0 to 6 point something. Actually 2 pi. 6.20 something. Okay. 2 pi. One full circle, 360. Okay. So I want to have some kind of space here. So it means that I want to extend my limit, my y limit downwards further. So I will start from negative 1.1 and then y max would be positive 1.1. Okay. So if I hit enter, what will happen? There's a little bit of increase, right? It's not much pronounced, but now the plots or the crest and troughs of the wave are not touching the upper and lower boundaries of your plot. So if we go back to our, if we go back to our presentation, okay, so we remove the unnecessary white space with the axis type command. Here is the ylim and xlim and ylim commands. Okay, so for the ylim commands, you just adjusted. Okay, we just adjusted the limit negative 1.1. So you just added a small space here, and at the top would be positive 1.1. If it is 1, your crest or your troughs will touch the boundary. Okay, and how about for the xlim? Okay, for the xlim, okay, we can also define the xlim, the x limit. So it means that it started from 0 pi to 2 pi. So the x mean would be 0. Then actually 0 pi, we can declare it directly. And then the highest or the x max would be 2 pi. But the problem here is this. What if I change my theta? What if I don't want to run my cosine or sine from 0 to 2? I want it from 2 pi to 4 pi. I will change this again, right? But somehow, there's some kind of programming practice that as much as possible, you want to change all of your what do you call this? All of your configurations at the top of the program. So for example, this calculate function, this would be the place you where you define all of the things. For example, the number of points, what is the function defined, and so on. And you don't want to change everything below the code, okay? Because you are now deeper into the code. So what you're going to do is that since you have a theta array, you need to access that theta array and get the smallest value. So what's the smallest value? Of course, it would be at the start because this is a lin space. You start from the 0, smallest value, up to 2 pi. So theta, and then of course theta 0. Okay, that's the start. Sorry, theta should be theta 1. Okay. Then theta n. Okay, the question is, bakit hindi theta 0? Why it is not theta 0? Because in MATLAB, we always start with 1. Okay? In the indices, MATLAB always starts at 1. Compared to Python, that starts from 0. So let's start. Let's run it. Okay. It doesn't change. It's still the same. Okay. So if you don't have any axis type, so let's comment this part. Okay, so axis type, you don't have axis type, you don't have xlim, you print it, it doesn't change. Probably because I already set this one. But yeah, I will try to do this. Okay, yeah. It's because I have GCA, so I just comment it out. So now I have this figure, I have this white space here, okay? If I allow uncomment this xlim, okay? If I uncomment this xlim and then press F5, you will see that it will do the same thing for the, it will do the same thing just like the axis type, okay? So whether you use xlim or axis type, it's okay. And for the practice, you can just use both at the same time to ensure that your plot, for example, you forgot to put your xlim, at least you have the x-axis type. Or you forgot the axis type, at least you have the xlim. Doesn't matter. Both options can be permissible. Okay, so let's go to next. Tick marks. Okay, this is a little bit complicated, but if you knew how for loop works, this would be easy. Okay, so now, if you look at the figure, I want to configure the tick marks. For example, this figure is running from 0 to 6. Let me run it again. Okay. From 0 to 6 point something. And in a publication, I don't want, or in any journal or even in my paper, I don't want my tick marks to run from 0 to 6.2 something. I want to run it with a uniform scale, uniform ticks. So for example, 0, 0.5, 1, 1.5, 2. For example, 0 pi, 0.5 pi, 1 pi, 1.5 pi, and 2 pi. For example, that's the thing that I want to achieve. We're going to have some kind of coding. Okay. So first is that we define an array of numbers. So this array of numbers will start from 0, okay? And then the step is 0.5, and then the endpoint would be 2. So this is a direct array multiplied by pi, okay? So this array will be our array to get our tick marks properly. And then we will have another array, but this array is different from any other array. This is what they call the cell array. So later on, I will explain to you what is a cell array. And then I will put an initial value to this cell array. The initial value of the cell array is 0, pi. What do you mean by this? Take note that in MATLAB, when you have these two quotations, it means that it is a string. So 0, pi means a string that has a 0 and a character pi. A pi that is in a LaTeX view, how you write it in paper, pi, that is pi. So let's go back to our slide. Okay. So, sorry. So we define first the T array. So your direct array has a value of 0, pi, up to 2 pi. And in numbers, it would be 0, 1.57, 3.14, 4.71, and so on. The next is you define also a cell array. So what is the difference between a cell array and just an array with a bracket? For an array, okay, an array can store values of the same data type. So for example, this first array here has a data type of all integers. So 1, 2, 3, 4, 5, 6, and so on. Negative 1, 2, 3, and so on. Also, the second array has elements of float. Okay, float data type 1.0, 2.0, 3.0. Anything is all about float. And then the last one is a string. This is a string array because you have string, uno, dos, tres. Okay. What is the difference of an array to a cell? A cell array can contain any data type. For example, you can have an integer together with a float, together with a string. So that's the difference between a cell and an array. Okay. So these data containers have different purposes. Cell arrays are really flexible when it comes to storing different data types, but most of the time, if you're just dealing with arrays, it is not advisable to use cells. You just need to use arrays. So going back, okay, you will define this for loop, and I will explain to you how this for loop works. Okay, but the end of this, or I mean, the result of this for loop would be this cell array here containing 0 pi, 0.5 pi, and 1.0 pi. And take note that when the for loop populates this cell and then you hit F5, okay, the program is now running. In the figure, you will see this kind of symbol, this pi. Okay? This is the LaTeX input for the Greek letter pi. Okay? So what we're going to do is this. First is that we type this command here. So first is that we define a for loop, okay? M as an index, okay? We start from 2. Later on, I will explain why 2. From 2 up to the last element, or you can get the last element by knowing the length, okay? So the length of t, okay? So the length of t is 5. There are 5. So 0, 0.5, 1, 1.5, 2. So the length of the entire t array is 5. That's why this length will give you 5. So from 2 to 5. So this for loop will run from the second element up to the last element, which is 5. Then we will set this, okay, this cell array. We will access the element m. Okay, we will access the element m of the L cell array. Okay, and then we will define, or we will put some kind of value, and this is the value num to string t of m, okay, divided by pi, okay, comma some kind of weird string 3.1f, okay, and then this is it first, and then we put it in a list, in an array, I mean, okay, with another string. Okay, if you're wondering what I'm doing, just calm down. I will explain this. Okay, so what does this code mean? Let's go back to our presentation. Okay, first we just made a T array, right? So this is your T array with 5 elements. Okay, as you can see at your upper right. To populate the rest of this L cell array, okay, we have already the index 1 value, which is 0 pi. We need to put 0.5 pi, we need to put 1.0 pi, 1.5 pi, 2.0 pi inside this L. Okay, and this L will serve as our tick label. Okay, so first is to get the length of t, which is 5. So the entire for loop will run from the second index up to the last index, or the last element. So here, as you can see, so you don't have the first element now. The next is that you get the second element for m equals to this one, and then divide this into pi. Take note that in your initial array, you multiply it with pi. So for now, you need to divide it with pi first, so that you will extract the 0.5. So after that, actually this is the operation. So t sub m, if m equals 2, so t sub 2, so second index, then the value of second index is 0.05 times pi. And then you divide it with pi, you will have, what's this? 0.5, right? And this 0.5 is a float type. It means that it is a number with a decimal, okay? Somehow, you want to convert this float type into string. Why? Okay, the reason is it is inside this bracket. And if you have this bracket, you cannot have a number and you cannot have a string together in a single array unless it is a cell array. So for us to have this float type 0.5, we need to convert it to a string. That's why we will use a command called num to string. And this num to string turns your number type or your float type to a string type. And you can also control the string formatting. How does it work? This one. So this string formatting is the same as if you are familiar with C programming. they're just using the same string formatting. So for example, you have a number 12.3456. And let's say you want to format this string as 7.2f. What does it mean by 7.2f? 7 means 7 positions available for the entire string together with the decimal point. Next is that the 2 would be 2 decimal points. You will allow 2 decimal points after the decimal point. Okay? 2 decimal places after the decimal point, I mean. And then the type of the data is fixed point notation. Okay? It doesn't change. It's not exponential, it's not scientific. So it's fixed point notation. So if we're going to apply it with our 0.5, this would be the case. So 0, 1, 2, we have 3 positions. Okay. We only have one decimal place. Sorry, it's not decimal point. 1 decimal place, and still is a fixed point notation. Okay. So it means that your 0.5 float type number will become now a 0.5 string. So it is now a string. Okay. So actually, you can also concatenate 2 strings together using this bracket. Okay, so you can have a string array, but you can also concatenate if you have only 2 elements. So if you have 2 elements here, you have a bracket, you can concatenate 2 strings together. That's why you cannot put a number here because it will result to an error. Just put another string to concatenate it together. And when you concatenate it, it means you combine these 2 characters. You will have a 0.5 and a character 5. Tada! You have a 0.5, 5. The interpreter of MATLAB will see this as 0.55. It will display like this. And then, you can now put it into the second index of the L cell array. And then you're going to repeat this process until the last T-ray element. For 3, that's 1.05, 1.5, 2.05. And now you already populated all of the places of the. So the question is this: how can we make the tick labels? Okay, so let's go back to our code. Okay, so first is that now you have this kind of code. You already have this L cell array, which are all which the elements are all strings. We will use each element from this L cell array to put it in each tick. And we're going to configure again the properties of your plot axis. Again, set GCA. Okay. Then there's a property called xtick. Okay. Your xtick will understand that your data will run from 0 to 2 pi. Okay. So T, this T array here, 0 to 2 pi. Okay. And then you can also configure again the label. Okay, the xtick labels. So the ticks would be this one. So let me show the plot. The ticks would be this one, this one, this one, this one, this one. And this would be all the tick labels, the numbers. Okay. So X tick label. Okay. And then put our cell array in. And then let's print it. Oops, there is something wrong. So what's something wrong? What's the error? Okay. Invalid expression. It means there's something that I haven't closed. Oh, where's that? Oh, look at this. There's something missing. So tm pi num to string. Okay. Oh, I should not close it here. Should remove num to string. Oh, no. I think I get it. This one. I should. So that's so done. So look at this figure. So now you all have the the labels from 0 pi, 0.5 pi, 1.0 pi, 1.5 pi, and 2.0 pi. Is this clear? Okay. So that's the purpose of this algorithm. Okay. The next is that we're going to apply this technique also for the y-axis. So copy and paste. But of course, since our values would be from 0 to 1, we don't need the pi. Okay? So we need to change something. Take note that our t array now will run from -1. Of course, we can still use the step size as 0.5, and it will be ended at 1, and then remove the pi. Then, of course, we don't need an initial value for the L cell array. We remove that. Okay, so you have an empty cell array now that you're going to populate it again. Okay, just like what we did in the x-axis. So now for the for loop, we will now start at the first index of the L array, and then again end at the length t. Of course, we will remove the over pi because we are not expecting any pi here. And then we will set set GCA, now y tick, and then next for y tick length. And let's hit enter. Oops, there's still pi because I haven't removed this pi. I'm so sorry. Again. Okay, so much better. So our plot is now becoming good. So you have now a uniform what do you call this? You have a uniform tick labels. You have now a defined pi here, and then from 0 to 1, okay, you have white spaces, remove unnecessary white space here, and so on. Okay, we can now add some kind of labels, but look at this one. Look at this 0.0. Somehow, if you want to plot anything, you don't want any decimal values with a 0. Whether it is 4 decimal places or so on, you just want 0 to be 0, not 0.0 or 0.00 and such. So we will redefine this code with an if statement. So an if statement is a conditional statement. So this is how you use if here. So if the element of t, this t array, okay, if the element of t, okay, is equal to 0, okay, so look at the sign. Okay, so in MATLAB, when you are comparing two values that are equal, the result is logical. You will use two equal signs. Okay. So if the t value, okay, whatever index, array index, or whatever index it is, and if the value of that index is 0, then let lm, okay, let that value in the cell array to be equal to 0. Okay, so this is now you are assigning now, but this should not be a number. This should be a string. That's why you put a what do you call this, apostrophe quotes. Okay, okay, then you need to close this if with an end also. Okay, so a command, I mean a control structure should be closed with an end. So if statements should be closed with an end. Of course, for loops, okay, these control structures, for loop, while loop, so on, should be also ended with an end. Okay. Okay. So what will happen? Let's play this. Let's run this. Oh, there's nothing happening. It's because it still follows this command. Because you just ended this, okay, but it will overwrite. You need to have an else statement. What do you mean by else? So if this command is true, then it will run. If not, then you should have a substitute, which is your entire expression here. Then close it with end. So finally, using this code, you hit it run, you will have this 0 to be 0, not 0.0. And okay, any questions? Oh, now our figure is becoming amazing. becoming decent. Now let's put some kind of labels. Okay. Let's put some kind of labels. So for the X, we can have X label. So where's my X axis? So you can have the command is called X label. So remember, if you want to label your axis, you have the X label and you have the Y label. X label would be, okay, let's say this is the angle. Okay. So it's a string. The title is the label would be a string. And then of course you might want a symbol slash theta. Okay. And then some kind of course, the unit is radian. And then you might want to put a label on your y. Y label which is equal to, okay, so let's call it a value, okay, and let's stick with it. And then that's it. So you have now a label angle, which is theta, okay, and then values. Take note that if you have this notation, slash theta, slash pi, there's another pi here, the slash pi in your ticks and so on, it means that it is referencing to the LaTeX interpretation. Okay, so LaTeX is another typesetting used for scientific. I mean, most of us is aware. Most of us are aware of using LaTeX. Okay, so the symbols are pretty close. The next, we should add a title. Okay, so let's set a title. So the title, the command title, okay, would be, let's say, sine theta, okay, and cosine theta. And let's hit, forget the semicolons, let's hit enter. Okay, so what you will have is this. You have a title, you have an X label, you have a Y label, you have a clear plot. Even if it's black and white, everything is clear. We can also extend our plot axis, okay? So I will add some. So set GCA again. And then I want my, let's say, the line width or the border to be thicker. So line width, okay, let's say around 5. Okay. Probably it's thick enough, or let's say 4. And then hit enter. And then you will have this. And I think that's the end of our professional. So take note, okay, that this plot here, whatever the size it is scalable. So you can enlarge this as this one. You can make it as full screen, okay. But in publication, the smaller the better, I think. But even if it is small, it should be still clear. The data is clear and readable. So again, you can use get and set again to change the properties of this. You can make it black, you can make the figure white, and so on. If you want to paste it in a publication that has a white background, change the figure color to white, so on. Later, I will show to you how to put latex or LaTeX writings here, okay, using the LaTeX interpreter. And that's it. So this is the 1D professional plot that we can now use. And technically, you have we call this the code, okay, that you can follow through, and then you can use this. Okay? You can use this code, okay, anywhere you want it. Okay, you just put the function here, and then just define the function here, and then plot it using this function. So that's it for our 1D. Do you have any questions? Do you have any questions? Okay. So I hope that you understand our 1D plotting. And for the last part of this MATLAB short course, we're going to do the 2D graphics. So for example, you have a 2-dimensional plot. How can we plot these 2-dimensional functions? F of x and y. Okay. So let's create 2D plots. So let's go back to creating 2D plots. So first is that somehow we want to make something as random as possible as our test function. So going back to our MATLAB, let's have another script. So new, and then script, or you can use the shortcut Control L. And then let's type 2D graphics. Okay. Then let us save this as 2D graphics. Okay. And let's hit save. But there's a problem. According to MATLAB, you cannot name your file with a number as its initial character. So you need a letter. Okay. It must start with a letter. So MATLAB, okay, we just revise it to the graphics. And then let us save this. Then, of course, just like what we did in the 1D graphics, I will just copy it. We should need to initialize MATLAB. Okay. And then let it run so that we could erase the memory, erase the command window, and then close all the figures that are not needed. Next, we define an array of numbers. Okay, array of numbers. Okay, so an array can be a one-dimensional array, or can be an m by n. Okay, m by n array, or can be a multi-dimensional array. Okay, so for now we're going to define an m by n array. So let's say a is equal to rand equals, let's say, 3 by 3. Okay. So 3 by 3. So if I hit enter, of course, I don't have any way to display this. So display this array. Array. So now I will use the image sc. Okay. So use image sc for the plot. And then hit hit F5 or hit run. So as you can see, you have this 3 by 3 array, and you have different values. Of course, let's put some color bar so that we would have an idea of what are the values. Okay. So now in the middle, it would be probably around 0.8. Okay. Let's compare it. So I will not choose semicolon. Again, I will hit F5. Okay. All right. Yeah. So you can compare the values of A here in the command window and the image sc plot. So take note that the first element would be 0.1874, which is near here, near below here. So it's a little bit dark blue. Okay. And then the first row, third column, probably 0.79. So it means that's really a bit yellow. And then I will run this over and over. So let me press F5 again. F5. What you can see, I mean, the values are changing, right? The values are changing. Again, F5, another set of random values. And F5 again, another set of random values. How can we fix this randomicity? We can still get a random value, but every time that we run the program, we will have the same set of random numbers. This is where what we call the rand seed will come into play. So rand seed 0. So what does it mean? So if I hit enter, okay, and again I hit the F5 again, and then I hit the F5 again, no matter how much I rerun this program, I will still get the same set of random numbers. So this is useful when we are testing some kind of algorithm. Okay? So we are testing our algorithm, we're testing our functions, our programs, and we want a random set of numbers, and we want to fix that random set. We use the seed. Okay, so we set the seed. We can set this to 0, to 1, and 2, and you will have different set of randomized values. Okay, so that's how the seed creation works. Okay, so this is the image function, as you can see. So 0.2190. Take note that our seed is 0, just like what we've seen in the MATLAB. So this is fixed. Okay, so each pixel or element has a color representing the values. Okay, so just remember that. Next, we want to make sure that our plot is, it looks good. It looks square as possible. Probably if we have an image like this is a little bit stretched, and we can stretch it like this one. Okay, and somehow you don't want this kind of configuration a little bit stretched. So we will use a command called axis equal type. Earlier we just used axis type. We will just add equal. Okay, so what would be the result? So axis equal type, and then press F5. So what you can see about the image SC, okay, it's now perfectly square because it's already typed and the axes are equal. Okay? So the lengths of the axes are equal. That's why you call it as axis equal type. Next, there's another function called pcolor. Let's explore that. Okay. So again, you have the image SC. Okay, this is a function that shows the image, okay, of your matrix. So you have this matrix, and then you just put it in an array, and then you let the image SC to visualize it as colors. Okay, like this, a map of colors. There's another command which is called the pcolor. They call it as the pseudo color plot. Okay, that's why they call it a pcolor, pseudo color plot. How does the pcolor works? Shift F5. Oops. For the image SE, you have what? You have 3 by 3 pixels, right? Like that, like pixels, but 3 by 3 box. Okay. But in a pcolor, you only have 2 by 2. What's happening? What I mean, how MATLAB solves this, or how other, even Matplotlib has pcolor. How does pcolor works? So let's go to the presentation. Okay. So the pcolor works like this. So this is our initial, this is our values of matrices. Remember that in the matrix, the initial matrix that we do have, the first element, first row, first column is 0.2190. Okay. But now in the pcolor, it's around here. It's below. What's happening? What's happening to the entire box? Okay. So there's a description here. The rows and columns of the matrix has shifted from the cell to the grid, and the matrix is flipped upside down. Actually, that's I call it the dumb explanation, but there's an explanation in MATLAB. But I understand it further when I compare the values. So let's try to visualize it. So let's compare image SC and pcolor. So you have a matrix with elements A, B, C, D, E, F, G, H, I. Okay. For image SC, okay, 1, 2, 3, 1, 2, 3, it means that each element will be filled inside the cell. Okay. So these are your grid lines. Okay. So that's how you fill the values of the squares in the image SC. How about in pcolor? So in pcolor, these cells will be turned into grid line. So 1, 2, 3. Again, this is 1, this is 2, this is 3. And then in pcolor, it will become pixel to grid. 1, 2, 3, 1, 2, 3. Okay? Then how about the values? So you get the matrix, and then you flipped it. When you flip it upside down, you will have ABC at the bottom, and you have GHI at the top. And then you fill the data of the pcolor. So that's it. That's how it is. That's how it works. Okay, that's how peak color works. And there's a use for peak color. Okay, there's a use for peak color. So as you can see, this is the comparison of image SE and peak color. So for your image SE, it just maps the entire matrix, but for the peak color, it flips the matrix, and you just get the somehow the first four corners. Of course, if you increase the resolution, you have now a uh, uh, for example, 500 by 500 matrix. Okay, the image SE and peak color will have uh, a further distinction because the peak color has its capability to create plots that are interpolated. Okay, so image SE is just your matrix, the value of matrix. But if you want a better visual of, for example, you have a smooth function, you want to visualize it with some kind of interpolation, you will use peak color because peak color is suitable for that. Okay, so let's go back to our MATLAB. Okay. So look at this. So this is our peak color. Okay. What if we increase the matrix, the size of the matrix? Okay. So let's say we make it as 50. Let's say 300. I want 300. 300 din nakalagay dun sa PowerPoint. So 300. Okay. And then let's run it. What you can see is there's a lot of lines. Okay. I mean, there's a lot of squares. Probably you cannot see it. Maybe it's blurred in your camera, but let's reduce it to 50. Okay. And then here, you can see it further. What can you see? You can see here that there are lines in between the blocks, okay, or between the cells. These are your grid lines, okay? The pixel to grid. So you have line. If we increase it to 600, what will you get? You will just get almost black. If it's compressed like this, everything is black. For us to avoid that, we need to use a command called shading. Okay, you can have shading interp. Okay, so when you declare a shading interp, it means that you're allowing the P color to interpolate your data. So how does it? So you just remove, okay? You just remove the grid lines, but somehow it looks weird. Okay, it is somehow looking weird. So let's compare image SC with P color with shading interp. Okay, so let's say 50 by 50, or let's make it smaller, say 30 by 30. Okay, and then I will have display this array using the color, and then I will also have a display using images. Okay. So using image. So image SC is now A. Okay, and the next is, of course, it is axis equal height. Okay, and let's have some again color bar. Okay, take note that if I press F5 again, you will see what you will see is just a plot of the peak color. There's no plot of the image SC. Okay, so I want to make sure that my figure will display two plots, one image SC on the left and one at the right. Okay, on the right. Okay, so I will just use what they call the command. Remember this, the subplot. So the subplot command tells us this. Okay, so there are three arguments or three inputs. The first one is the number of rows. I only want one row in the figure window. I want two columns for my two figures. okay, side by side. And the first figure would be image SC. So I will put it as 1. The next, how about the second one? You have subplot. Of course, again, 1 row, 2 columns, and the second column. Okay, and press F. So you will have your image SC. Okay, as you can see, you have the image SC and you have this P color comparison. Okay, so this one has a shading interp. So somehow, if this looks ragged and looks rough because this is not a smooth function. But if you have a smooth function that I will show to you later on, okay, P color, you can appreciate P color more. Okay? But in most aspects, we will use image SC. Okay, so that's the comparison of P color and image SC. Okay. Of course, somehow I want to no, it's not necessary. I just want to flip the axis, but you already knew that. Okay, now going back. So don't forget to use shading interp again. Don't forget to use shading interp when you're using P color if you want to have some kind of interpolation, smoothing, and such, and removing this black line. Okay, so this would be the view of your P color. Okay, now we're going to create a grid. Okay, we're now going to create a grid. So going back, so let's make this as comment. So there are 2 ways of commenting a line or lines. So you can select all, okay? Then you can right click comment, or you can just use the shortcut Control R. Also, if you want to uncomment things, you can use again right click uncomment, or you can use the shortcut as Control Shift, and you can just enable this one, not comment. For now, I will comment this. Okay. Now we will build our plotting grid. Okay. Building the plotting grid and the function. So now we're going to build some kind of function. This is just a test function, a smooth function that when we put here into the 2D graphics, it would look nice. Of course, you can have any kinds of functions. For example, you have a function of temperature gradient, and your temperature gradient is 2D. Of course, there are maxima and minima, but just flat. You can use that. You can use this technique to plot those functions. So now we will define an arbitrary or randomly generated function. We will build the grid on where we're going to plot this function, and then the rest would be just tweaking the axis, the ticks again, just like what we did in the first graphics. Okay. So first is that we build a physical size of your basic physical size of your grid. Okay. Let's have it as Sx. Let's say it's equal 2, and then Sy equals 2. Okay. And then we have also the numerical width, which is Nx. Okay. What do you mean by numerical width? It is the total number of points along a certain axis. For Nx, let's say we declare that there are 128 cells, okay, along the entirety of Sx, okay, which has, let's say, for example, a dimension of 2. What 2? Maybe any other units, meters, centimeters, and so on. Okay, it doesn't matter. Just make it a scalar. You just have a standard physical size of 2, and then you divide it with say 128 number of elements. Okay, and then ny. Your ny would have this code: round, okay, nx sy over sx. What does it mean? Let's go back to our presentation. Okay, now in MATLAB, we can create a grid like this one that we can populate each element with a certain value. So we need to know about the grid's physical size, the grid's numerical size, the grid resolution, the grid axis, and the data that we need to put inside the array. Okay? So this is the grid's physical size, is x and y. So the entire length of the x and the entire height of the y. For the numerical size, it's nx and ny. Take note that these values must be integers. Okay? You cannot have a 0.5 cell. You can only have a single cell with an what do you call this? You can only have a single cell. It's a defined cell. It should be an integer. So 1, 2, 3, 4, 5, 6, 7. You cannot have 128.5. Okay, 128.5 nx. All points, okay, the all number of points must be an integer. Next is grid resolution. Your grid resolution is dx and dy. Okay? So you get one cell, dx and dy would be the dimension of that single element cell. Okay, and the next is that there's a relationship between the grid parameters. Obviously, if you have a physical size Sx, it means that for you to get that, for example, you have nx and dx, you need to multiply the length dx to the number of the elements. So 428 times, for example, your dx, the side of your element is 1. So the entire length of Sx would be 128. But in our MATLAB graphics, most of the time, Sx and Nx are specified at the start of the program, while dx and dy are calculated. Because this dx and dy can adjust themselves. Okay? So if we define Sx and Nx or Sy and Ny, we can control the size of a single element. We can make it as small as possible, giving us a higher resolution, or as huge as possible to have your plot or grid low res. Okay. So this round nx times sysx ensures that our square cells will be remaining squares. Okay. The cells will be as square as possible. If sx is less than sy, then ny is greater than nx. Okay, and vice versa. Okay, so if sx is less than, for example, sy is 100 while sx is 10, it means that your ny would be as large as possible. There are more cells along the y compared along the x. Okay, so the round function ensures that ny is an integer. Okay, just like nx, because if you have a decimal, if you have a fraction here, a float, and then you multiply it with an integer here, it might become a float also. Okay, so to ensure that there would be no float or no decimal numbers, no fractions, you use that you use the code round. Okay, so next is the random function generator. Okay, I can just copy this. Okay, I can just copy this one. Let me copy this one. There's a lot of this to type. Okay, and don't worry, it's okay if you don't understand this. This is just a test function. Random function generator. Okay, so as of now, I just put it there, but I want to tackle this also. Okay, so now we have a physical size of the grid where we can put our function. Where's the function? Here's the function. So this is the algorithm to create this plot, this data here. Okay, so now I will describe to you step by step how it becomes possible. So random function, we start at f0.2. What is f0.02? This f0.02 is the control of the amount of mountains and valleys. What does it mean? Look at the image. So if your 0.1 is large, you have a lot of figures here, a lot of points here, that's up and downs. But if your 0.01, if your f is low, okay, like 0.01 0, 0, 1, you can see that you only have one mountain, less than a little bit high, but some areas that are low. Okay, it talks about the speed of randomicity. Okay, so that's the control of your F. Okay, so this is just the math. Okay. Next is this one, NX1. What do you mean by NX1, and what do you mean by this code? Okay, so first, NX1 is our starting index. So this is where we start counting to the entire grid. Okay. So NX1 is 1 if your F equals 0. So if you have this equation, this F is 0, then you only have 1. Then if your NX1 is equal to NX, it means that you give the last column, okay, F is equal to 1. Okay. But you can see there's a weird factor 0.9999 here. What does it mean? It's because if you don't put this 0.9999 here, your NX1 or your starting index, if F is equal to 1, will exceed the total number of elements along the X, which is 128. It will give you 129, which is out of bounds. It will produce, or it will throw an error in MATLAB. So you make sure that you have 0.999. And since you have 0.999 as a factor, you need to use the floor. Okay? Why not the ceiling? Because if you use the ceiling function, you will go to 129. If you go to round, if you use the round command, and your answer is around, for example, 1.285 or 1.286, and you use round, it will go to 129 also. So to ensure that the value will be staying at 128, you need to use the floor function. Okay, so that's it. Next is N2. That would be the stopping index here. So NX1, NX2. Okay. So how does it, what is the relationship of your NX1 and NX2? So you start at the end. So this is your NX. You subtract with the amount of NX. For example, your NX is 3. So you subtract 3 to, let's say, this is 10. Then you have 7. And then add 1. You will have this NX2 as the stopping index. Same case for NY1 and NY2. Take note that the NY1 is above and NY2 is below because we are dealing with matrices as of now. We don't have the Y dir. Okay, we don't use the Y dir to flip the entire matrix up and down. So the counting will start at NY1 going down to NY. The next, since we have NX and NY, okay, as the numerical width, for example, we have 128 elements along the X, 128 elements along the Y, then our function must also have the same dimension. And we will use the rand function to create some kind of random function. Okay. Take note that in this case, that the color bar is from 0 to 9. So 0 to 9. Actually, it's actually 1.0. Sorry. So 0, 0, it should be 0.0 to 1.0. Sorry, this is wrong. Okay. Now, I need to have some kind of offset. Okay. Minus 0.5. What does it mean? We need to shift this entire the entire function with minus 0.5. How does it work? So remember that you have an n by n matrix. For example, this is 3 by 3. That's just example. Nx is 3, ny is 3. You have a 3 by 3 matrix. So for example, your values for 3 by 3 matrix would be all ones. 1, 1, 1, 1, 1, 1, 1, 1, 1. And then you introduce this minus 0.5. What will happen to the entire matrix? That minus 0.5 will be distributed to each element, and you will subtract 0.5 each element. So 1 minus 0.5, 1 minus 0.5, 1 minus 0.5, and so on, until you populate the entire matrix. And that's what will happen to this matrix F. Okay, that's why the color bar color bar is now shifted from 0 to 1 up to negative 0.5 to positive 0.5. And there's a reason for that. Okay, so all the element values are between 0.05 and between negative 0.5 and positive 0. What's the reason for that? This one. Okay. So this random function, okay, uses the two-dimensional fast Fourier transform. Okay. So you have this entire matrix, and then you will use your Fourier transform to create some kind of these values. Okay. And if you do not have, if you don't shifted your entire function, okay, your entire random function with negative 0.5, you just don't shifted it, what will happen? You will get this one, this peak. So this corner is already zoomed in. Okay, this peak has a very high value, around 8,000, and you cannot actually see all of the other values. It just just very small. So yeah, around 20 to 100, less than might be. So you cannot see, cannot get anything from this because of this value, this peak. They call it as a DC offset. Okay, so you want to remove that DC offset. Uh, this time you want that offset. You want that DC offset. I mean, so that you could actually see the randomized value. That's why you need the negative 0 point. Next, now you have the fast Fourier transform. Okay, this is the result. Okay, as a review, this is the Fourier transform. I think most of you, lahat naman tayo alam yung Fourier transform. So no need to review this. Okay, let's go to the next step, which is masking. So this is where our random function will take shape. So we will mask, we will retain the randomicity from these few first few columns, and then at the last few columns. Okay, and then anything in the middle will be set into 0. And same case for the y. For the y, you will also mask them. You will also set them into 0. You will only have values at the very corners of this entire space. And if we use an IFFT, which is they call as the inverse fast Fourier transform in 2D, okay, you will get this beautiful random. Okay, and you get the real, because when you do a Fourier transform, you have the, of course, the real and imaginary values, and in MATLAB you cannot plot them at the same time. So you need the real command to get the you need to use the real command to get the real values of this IFFT. So that's the random function generator. Okay, so let's go back here. Okay, so let's try to run this. Let's close this one. Okay, so when I run this, there's nothing wrong. It means it doesn't throw an error. It means that we're all good. Now we want to display this random function. Okay, so how can we do that? First is that we need some kind of function access. Okay, so function access. So now I'm at a very, very low, so I will just put some empty spaces here. Okay, and then put some function access. Now we can define dx, and we can now define dy. What is the size of the element, of a single element? What would be the dimension of each element? That would be sx over nx, and sy over ny. Okay. So what's the use of this function access? You will use this when we define our grids. I mean the tick marks. Okay, so there's what you call the axis vectors. Okay, or axis vectors. So the axis vectors tells you about a certain array that each cell would have that value. Okay, so for example, XA as an axis vector. So you define 0.5, okay, up to n minus 0.5 nx, okay, times dx, and y is equal to 0.5, okay, ny 0.5 times dy. You might ask, what's the meaning of that? Let's go back to our presentation. Okay, so axis vector. This is really important for the axis vector. Take note that the physical width of the pixel would be can be solved or can be calculated using sx over nx and sy over ny. Okay, but what is xa and ya? So look at this grid. Okay? Look at this grid. Take note that all of the data will be put inside this we call this inside this box. Okay, boxes. Okay, so there would be some kind of value here, there's some kind of value here, and so on. But if we do not use this axis vectors here, okay, you will not get a Cartesian coordinate related grid. Why? Look at this. So we started at 0.5. Okay, here. So the 0.5 is that's the coordinate of the first block. 0.5, 0.5 for the x, 0.5, 1.5, 2.5, and so on. But look at the lines. Where are the lines? 0, 1, 2, 3, 4, 5 along the x, along the y. So the grid now mimics, it retains its Cartesian coordinates. Okay? So what will happen if we start at 1? For example, xa equals 1, then 1 from nx, okay, times dx. It would look like this. You will start at 0.5, not from 0, not from the origin, and everything will be shifted. In computational electromagnetics, or when you are going to design some devices on the grid now, it would be problematic. As of now, probably okay because you're just plotting functions, but in the future application, in the building geometries, in data arrays, we need to specify this as it is. We need to specify our axis vectors so that we will retain our Cartesian coordinate system. Okay. So next, tick marks. Okay. So let's go back here first. Okay. So first, let's draw the function now. Draw the function. Okay. So we're close. We're really close. So image SC. Now your image SC can take 3 arguments now. So first is the XA, next is the YA, and then next is your, of course, the function F. Okay. So now your F is this. Okay. This is your F, your already randomized function. Okay. And then let's put some kind of color bar. And then of course our axis equal type. Axis equal type. Let's say we want to flip. Okay, we want the Cartesian configuration. So GCA again, and then the wider again, the wider property, and then let's set it to normal because image SC, the default is reverse. F5. Oops. There's some kind of error. Okay. Oh, equal. Sorry. It should be sorry. Okay. So now we now have the printed function. This one we have the printed function. Okay. So what's next? Okay. So we already have the image SC. Since this function is a smooth, locally smooth function, at least in the figure, it somehow has a smooth gradient from the crest and from the trough. Okay, let us use the peak color. Okay, let us use the peak color. Okay, and again, shading interp to remove that. Shading to remove the line. Shading interp, we just put the interpolation also to increase the smoothness. Okay. 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 Somehow there's a problem with MATLAB when uh you are displaying things. What is it? This figure, if I don't have it here in the PowerPoint, but this figure, for example, you have an arrow. You want to display an arrow upward. Okay, so that's your figure, an arrow upward. Your MATLAB, your image SE and P-color will not show that to you. It will show something like flip to the side. Okay, that's why it's a common practice when you're using image SC, okay, or P-color, to put this one, dot apostrophe, this one, dot apostrophe. What does it mean? What does it mean by dot apostrophe? This is what they call as the Hermitian conjugate. Well, it's a mathematical term. It's just a transpose. It's just a transpose of the matrix. So everything you just need to transpose everything. Okay. So this the if you have complex numbers. So for example, this f, you don't take the real. You have the combination of the real and the imaginary number. If you do this, f dot then apostrophe, you're getting the complex conjugate. Okay, transpose. Complex conjugate transpose, so the Hermitian transpose. But since our f has already real values, it doesn't matter. It will just transpose our entire matrix. And so that's it. So for example, you have a row column, you transpose a row column, it will become sorry. If you have a row vector, and then you transpose a row vector, it will become a column vector. Okay, so let's print this. Okay, it looks nice. And then our practice is to change the tick marks, okay? Edit the lines, okay? Edit the tick marks, edit the ticks, okay? And then the border, so on. Put some kind of labels, X and Y, and put some title, okay? So now, let's do it. So, let's have set view. So we're close to finish this. Okay. So again, axis equal type already here. And let me just copy this. Let's move it here for proper documentation. Okay, let's have the x-axis, and let's have the y-axis. Again, just like what we did in the 1D plot, we're going to get this function, okay, to control our limits and to control our ticks. Okay, we'll just get this one, okay, and just paste it here. Okay, so just so that I will not type, and then same case for the y. But of course, we will edit the limits. So now we define this entire grid using the physical size Sx, and we want to show that this entire square space, okay, this entire grid will run from 0 to 2, just like this, 0, 0.2, 0.4. But for example, I just want 0, 0.5, 1, 1.5, and 2. I don't want many tick marks. Okay, so we will just do it here. So of course, in the x lim, you will get the lowest value, which is 0, and then the maximum value, which is Sx. That's the end value. That's the physical size, Sx. Okay, and then your t will run from 0, and then the step size is 0.5, and then the end value is Sx. Okay, so 0, 0.5, 1, 1.5, and then 2. Sx is equal to 2. And then your L array will be empty. Okay. And then let's just do this like this one. Okay. you will start with the first array element, and then I think it's okay. This is okay already. Let's edit ylim. Of course, you start from 0, and then you will end up at sy. Okay, I think you have it right here. Okay, sy, and then you start from again from 0 for the t array. Then the step size 0, 0.5, 1, 1.5, 2. So sy, and then empty array. I think this is okay. Okay. Oh, there's pi. Should remove this pi. Sorry. Okay. Okay. So look at this. So you have these tick marks along the y. So 0, 0.5, 1.0, 1.52. But along the x different because I think didn't able to remove the over pi here. Let's run it again. Okay. Much better. Okay. So 0, 0.0, 0.5, 1.0, 1.5, 2.0. Again, just like in the y, you have 0 here. Okay. 0 not 0.0. If you want to remove the 0.0, you need to do what we did in the y-axis. We need to implement this code to your x-axis. Okay, but actually, there's another way, okay, of removing zeros. If you run this, oops, sorry, not indented. Oops. Okay, if you run, oops, sorry, there's no end. Sorry. So if you do not have any end, it will throw an error. So you don't close it. So if you look at this plot, you have double zeros here. 0, 0, 0, 0. It doesn't look good. Probably you want to turn off one of the zeros. So I will just remove 0 here. I will just put put an empty string like this one, and then press F5. Okay, and then after press F5, I have 0, 0.5, 1.0, 1.52, and then the same case for y. So somehow I want to change the font size. Okay, so what should I do? Get GCA again. So sa set view, get set GCA. Okay, GCA font size again. Okay, font size, and then let's make it big, 18, so that we could see the tick marks. So like this one. Okay, so you have these values here. Okay, 0, 0.5, 1.0. Okay. It looks nice now. It looks big. Okay, probably there's another thing that I want to change. Let's change the line width further so that we will have a thicker boundaries of line width. Okay, let's make it 4 or 5. Let's make it 4. Okay, so you have this one. Okay. Okay. The next is label. Okay, so for the x and y, we put labels. Okay. So x label is equal to x-axis. Okay, and then for the y label, you put y-axis. Then hit enter. So sorry, should be y label. So x-axis and then y-axis. But somehow I want my x to be slanted, okay, and my y-axis to be slanted also, or italicized. Okay, so I can put a $sign, okay, on the both sides of your x and your y. Okay, and then press F5. So as you can see, doesn't work. Okay, somehow there are $signs here, but it is because we didn't we didn't use an interpreter to interpret this symbol. This is a symbol for math notation and LaTeX. or in LaTeX. So we need an interpreter. So interpreter, then put LaTeX. Okay. And also do it with the Y label. So interpreter, and then LaTeX. Actually, you can LaTeX. And then run it F5. So as you can see, okay, you have the x-axis and the y-axis in the LaTeX format. Okay, you can also increase the font size. So again, we will access the properties of the X label. Okay, so font size, let's say 22. Same case for the Y label. Font size 22. It already knew what's on my mind, and let's hit enter. Actually larger. We should make it larger, maybe 27. 27 is the default size, maybe 30, maybe. Yeah. So you now have greater. So it's because of the GCA. We have GCA 0.18 here. Anyway, excuse me. Okay, so we already have the X label and the Y label. The only thing that's left is to put a title on this function. Okay, so let's say it, okay? Just like a 1D graph title. So of course it's a string. We can use LaTeX. Okay, so this is a random function. Okay, let's say random function, and then let's say you want to put the equation inside of your title. You put a double dollar sign, and then you put the function. Let's say f of xy is equal to, let's say, some kind of random function, not necessarily equal to that smooth function that you see in the plot. Let's say 3x squared, 3y squared. Just that. And then use the interpreter, and then put LaTeX. And then let's say you increase the font size to, again, 22. Font size. Actually, you can use enter, okay? Or you can type triple dot if you want to write a continuous code on the new line. Okay, don't forget the triple dot or the ellipses if you want to make a multi-line code. Okay, font size would be somewhat 20. Okay, so this is the final piece of the code, and let's run it. This is the result of our function. This is the 2D plot that we produce. We have the labels, we have controlled y ticks, everything. Okay, we have the random function. Everything is here. The color bar. You can also edit the color bar using the get and set. Okay, set GCA or set color bar. Set define a handle again to access the plot, the plot axis and the figure window, and so on. Okay, so in the presentation, I think that's the end. Plot title, and this is the 2D professional plot. Here, it's a different plot. It's the same plot, of course, because the random seed is 0. Okay, just change the title, okay, and so on. So again, you can rescale. You can rescale this till square. Okay. Okay. You can make it small. You can make it large. Okay. Still, the details can be read. It's clear. Okay, so we just finished our introduction to MATLAB graphics, our 1D graphics and 2D graphics session. Okay. And next time, once we launch the short course part 2, we're going to create shapes. Okay, so we have the MATLAB short course part 2, which is building geometries into data array. So you have mesh grids, you will be making primitive shapes, linear mesh grids, rectangles, lines, fields, radial mesh grid. What is a mesh grid? Okay. Circles, ellipses, rings, azimuthal, mesh grids, Boolean operation, and or XOR, XNOR, or not everything. And then you can create exotic shapes that you can then coordinate rotation. You can rotate all of these shapes, combine all of these shapes, even make a Mickey Mouse. And if there's time, we will have another short course part 3 for creating 3D graphics. Right? So the only thing that is in plan is part 2, which is 2D figures, and then maybe part 3 of the short course would be focus on creating 3D graphics in MATLAB, exporting this model from MATLAB to CAD and vice versa. It would be really an interesting subject. And this is the end of our MATLAB graphics. Thank you very much for attending. I hope that you've learned a lot of things, even though you already knew how to use MATLAB. I hope that this will help you implementing your own MATLAB codes in the future. So thank you very much. So Paolo, you can take the lead.
Thank you also, Francis, for giving a very detailed talk about MATLAB graphics. Sure, let's have a little Q&A. If there's any questions that the audience would like to ask, you may do so.
Tanong lang po kayo. So you can ask any questions. If you're interested in MATLAB, something that you're implementing, you can ask me anything. Wala na. Wala naman silang tanong.
Okay, if there is no questions from the audience, sige, once again, thank you, Francis. We will be emailing an evaluation sheet for the evaluation of this event by email. So any feedback would be highly appreciated, especially moving forward if we decide to um, make more content like this or to add more into the course and things like that. So yeah, I guess there's nothing else from my end. Once again, thank you everyone.
Thank
And
you.
one last thing
Okay.
pala, the resources and the recording of the video is available upon request. But for the optics and research, for the optics group, I think I will be uploading it into our GC for everybody's references. So yeah. So once again, thank you everyone for attending. That's it for our short course in MATLAB graphics, and have a nice day.
Thank you. Thank you.